Hello, Chem1B. This is our solution chapter video 4, and we're going to be talking about primarily like dissolves like and solubility between two liquids. So things like adding, ethanol and water together. These are both two separate liquids. Will they dissolve in one another? Won't they? Type of thing. We can use the like dissolves like rule to figure out whether a substance will dissolve in another substance. This is slightly different from the solubility rules that you learned in Chem 1A for whether an ionic compound will dissolve in water. This is more another liquid dissolving in another liquid type situation. Now, what the like dissolves like rule basically states is that materials with similar intermolecular forces are going to be soluble in each other. So like intermolecular forces between the two things will dissolve other things with similar or like intermolecular forces. Now, in high school, I think it's commonly taught as something like polar molecules with other polar molecules versus non-polar molecules with non-polar. All right. Now, this works pretty much because when you have polar molecules, their IMFs generally are pretty similar. They're not exactly the same, um, but they're usually pretty similar. Nonpolar molecules also have similar IMF to other nonpolar molecules. So this is serviceable. It works 90% of the time. It does miss a couple things. So that's why in this class, we're going to think of it more in terms of their intermolecular forces, which is close to polar versus polar, nonpolar versus nonpolar. So when we have something that's like a substance with IMFs that are very different from the substance we're trying to mix it with, they're probably not going to be soluble to any great extent with each other. So that's the like dissolves like rule. Now, one thing you do need to understand about this whole system is how substances actually dissolve in one another. Now, if I just have a container of water, all the water molecules in that container are going to be attached to each other via all their intermolecular forces. Now, in water, we have London dispersion, we have dipole-dipole, and we have hydrogen bonding intermolecular forces. And so all the water molecules are going to be kind of stuck together via those intermolecular forces. Now, if I put a new substance into that water, what has to happen in order for that substance to dissolve is the water molecules need to start forming intermolecular forces with that other molecule that we've added. So for instance, let's say we added ethanol. Ethanol also has London dispersion, dipole-dipole, and hydrogen bonding. So it's going to be soluble in water. And this is because the two water molecules, they're going to have to break apart, and then they're going to have to go attach themselves using intermolecular forces to this new solute that we've added to the system. And so this is only going to occur when the attraction between the molecules with themselves is weaker than the attraction with the new molecule. And so that's when we're going to see solution formation.
You should also know two definitions known as miscible and immiscible. Miscible liquids are very, very soluble in each other, but that's not even enough to really get the full picture. They are soluble. Two liquids that are miscible are soluble in each other at any proportionality. Ethanol and water are a perfect example of this. And I'm going to use alcoholic beverages as an example, as my to kind of describe this. So beer, most like regular over the counter like trash beers is what I'd call them, like Coors Light and stuff like that. They're around 2 to 4% ethanol. If you're drinking like really good beer, like craft beer, IPA and all that, they can get up to a max of around 10%, but that's pretty rare. Most beers are in the 6 to 8% alcohol region. So water is by far the solvent by a large margin. But if we look at like wine generally you're around 12 to 16% ethanol present in that, and the solvent's still water. But you can see that there's a lot more ethanol in wine than in beer as a general statement. If we get to hard alcohols like vodka is 80 proof, and if you don't know anything about alcoholic proofing. Here's a life lesson. The proof is 2 times the percent. So if you want to calculate what the percent of your alcoholic beverage is and you know the proof of it, then divide by 2. That's your percent. So 80 proof vodka is 40% 40% ethanol. Now, still, water is the solvent, 60% probably mostly water, and then the rest ethanol. However, then there's the Bacardi 151, and that substance, the proof is the 151 in that beverage. So if you do a quick calculation there, that means your percent alcohol is 75.5% ethanol, meaning water in that beverage is technically the solute, not the solvent. And so you can kind of see these two substances are very soluble in one another, so much to the point where it doesn't matter which one's the solvent or the solute, they'll dissolve fully in one another. Immiscible liquids are exactly the opposite. They're pretty much never going to dissolve. If they dissolve in each other at all, it's incredibly low solubility. Gasoline in water is a good example, or oil in water. So you should know how temperature affects solubility. So for ionic compounds, generally, as a general statement, as temperature increases, so does solubility. There are some few exceptions out there. For instance, sodium sulfate, you can see its line is decreasing as temperature increases. So the solubility of sodium sulfate actually does decrease with increasing temperature. But that is a very rare situation. Almost all ionic compounds increase in solubility, in water at least, when temperature increases. And you should know that.